For his bewildering responsibilities to the fields of material science, Kaku has really referenced that the James Webb Space Telescope has seen 6 enormous planets that specialists recognized were unequipped for existing. These examinations have the authenticity to open up new points of view on the manner by which we could decipher the universe. The straightforwardness is both enrapturing and meekly testing existing hypotheses about the new turns of events and the development of universes. It deduces a staggering game plan to pay extraordinary respect to these updates. Atesh and the statements by such prepared experts highlight the meaning of these divulgences. Kaku is a shocking figure in the scientific field. A physicist of American and Japanese heritage, he is viewed as a specialist in both typical material science and quantum mechanics. Instead of some more moderate and dubious subjects, Kaku has been open to the amazing, prideful possibilities of the James Webb Space Telescope mission. His energy to embrace new discoveries and share them with the public shows his obligation to driving our appreciation of how we could translate the universe. We are grateful that this obvious expert has decided to end his calm and clearly share what can no longer be denied. The strong, clear tone of the momentous physicist is evident in his comments on the revelations made by the James Webb Space Telescope, giving the likelihood that this has been a progression that has reignited his interest. Join us as we examine the repercussions of Kaku's transparency about these 6 titanic plans. Kaku is an expert who has reliably had the ability to examine new hypotheses. Throughout his life, he has shown a responsiveness to ideas that challenge conventional thinking, understanding that Einstein's theories of relativity and Newton's laws, while essential, are limited in fully grasping the universe's complicated plan. Kaku believes that the revelations of the new telescope could transform the field of cosmology. However, many of his colleagues still cannot embrace this view. This has caused concern and skepticism among Big Bang scientists and critics of quantum mechanics. Yet, this only draws laughter from Kaku. The James Webb Space Telescope has revealed 6 giant galaxies dating back to the earliest times of the universe. Each of these immense systems contains more stars than our own Milky Way, despite having formed merely 200 to 700 million years after the Big Bang. The group of cosmologists who made the discovery has named these splendid, massive structures universe breakers. If confirmed, they would fundamentally change how we understand the universe. The implications of these discoveries are significant, suggesting that the universe's early years were far more dynamic and complex than previously thought. The theory of how things began tells us that the universe was tumultuous after the Big Bang. The first massive objects took a long time to form, and it took even longer for these objects to reach sufficient density and produce light. The development of complex structures like galaxies was thought to have occurred much later. Some of the recently found giant structures surpass the Milky Way in size, and their immense brightness suggests they were possibly forming thousands of new stars annually. In contrast, our galaxy forms stars only sporadically. It remains unclear exactly when the first structures formed, and experts have not yet settled this question. One thing is clear. At the beginning, there may have been only individual stars or groups of stars that eventually merged into larger structures over time. Smaller galaxies supported larger, more massive structures. Previously, it was believed that such enormous and complex systems were incapable of existing at that time, raising questions about whether the universe is significantly older than previously recognized or if such colossal systems formed much earlier than anticipated. This scenario is difficult to reconcile with conventional science, which still finds issues with this model. Some areas of material science have explicitly dismissed these discoveries and questioned the accuracy of age estimates. Kaku is aware of this and had this to say: there are different models and old theories that persist due to the influence of certain established experts. Many of these theories were scientifically debunked when critical research revealed their flaws. The truth in any science, especially in material science, lies with the work of experimentalists who keep theories sharp and on track. He went on, "Here on Earth, we have very little data about the true origins of the universe. This statement underscores the importance of continuous testing, updating, and reaffirming in the scientific process. The theory of how things came to be was first outlined in 1927 based on observations of the universe's expansion. This information led to the conclusion that the universe started from a single, unimaginably dense point and has been expanding ever since. At the time, it was difficult for people and scientists to imagine a universe with both a beginning and an end. The possibility of an eternal universe was beyond human comprehension. Even today, scientists still struggle to fully grasp it. However, it is essential to consider these possibilities, even if the new revelations do not align with what experts have accepted for decades. Science has demonstrated time and again that reassessment and openness to revolutionary ideas are critical to the scientific process. For instance, when Einstein was young, it was widely believed that stars and planets were fixed in the universe and that these particular arrangements occupied a defined space. But now we know that everything in the universe is moving. Planets orbit stars, stars move within their galaxies at speeds of several kilometers per second, and entire galaxies move rapidly through the universe, whose ultimate destiny we still cannot predict. This profound understanding of the universe challenges long-held beliefs and highlights the need for continuous inquiry and adaptation in our scientific thinking. This dynamic understanding of the universe emphasizes the necessity of constant questioning and the evolution of scientific theories. Researchers today face the challenge of identifying anomalies and ensuring that theories are robust until they are thoroughly tested or confirmed by observational data. The idea of the Big Bang emerged from the observation that galaxies are moving away from each other, with this distance being proportional to their separation from Earth. This concept, known as the Hubble law, suggested that the universe has been expanding over time. Factors such as cosmic microwave background radiation and the redshift of light from distant galaxies, alongside other cosmological phenomena, appear to support this theory. However, it is essential to remember that in the past, people also had observational evidence for beliefs that we now know to be incorrect, such as the Earth being flat or the Sun revolving around it. These misconceptions persisted until new events or technological advancements provided a clearer picture. Today, we find ourselves in a similar situation. Researchers anticipated that the James Webb Space Telescope would confirm questions related to the Big Bang theory. Instead, it has presented findings that challenge the established narrative. The discovery of 6 massive galaxies, seemingly impossible according to current models, underscores the ever-evolving nature of science. This demonstrates that science is a continuous process, requiring experts to remain open to new discoveries and willing to revise existing theories based on available evidence. These groundbreaking findings have tested current understanding and prompted a reevaluation of long-standing cosmological theories. Scientists use redshift as a tool to calculate various measurements in the study of the universe. Redshift, also known as the Doppler effect, refers to the change in the color of light as light sources and observers move relative to each other. To understand this, imagine standing still and hearing a car approaching. As the car gets closer, the engine sounds louder, but when it passes and moves away, the sound changes. This occurs because the sound waves change as the car moves. The same principle applies to light. When a light source, such as a distant star, moves toward us, the light shifts to bluer tones. Conversely, when the light source moves away, the light shifts to redder tones. This phenomenon is called redshift. Physicists have converted redshift values into rates and distances for analysis in the study of the universe. However, it is crucial to note that even a small error in these calculations can have significant consequences. The previous assessment methods are now under scrutiny. The latest discoveries related to our universe require consideration of whether they are truly based on redshift errors or if some researchers are merely dismissing current realities. This question demands careful evaluation and a meticulous review of the data and methods used in the analysis. The ongoing assessment and reassessment of measurement techniques highlight the growing understanding of the importance of constant inquiry. The James Webb Space Telescope has provided a new lens through which to view the universe, uncovering extraordinary insights into its early development. As scientists continue to analyze the data, the implications of these discoveries will undoubtedly shape the future of cosmology and our understanding of the cosmos.